Hello everyone. Today in this session we will understand the FEA one-dimensional bar problem. In this one-dimensional bar problem we will try to figure it out these three things: displacement, strain and stress. This is the very general and simple example, but after this example you will be able to understand the complex numericals related to FEM also. So let us begin. I suggest that as I am explaining you just also keep a pen paper with you and start doing the practice with me, so you will remember all the steps. I will show you the number of steps and you just need to follow those steps in future and you will be able to solve any kind of bar problem. So let's begin. So I'm just starting it with the reading a numerical. It says that calculate the displacement, strain, stress for the following bar as shown in figure. So now you can see that there is one bar which is fixed between two different walls. Now you can see that here are two different walls are here. So you can understand that this bar is fixed at both ends, and in numerical also they are saying that its elasticity is 2 into 10 raised to 5 Newton per mm square. The area of the bar is given as A is equal to 300 mm square, A2 is equal to 100 mm square and A3 is 300 mm square. Also understand that at this point we are applying a 10 kilonewton force, and here is also at this point we are applying a 5 kilonewton force. The length of the bar is total 600 mm. You can see that it's 200, 200 and 200. So this is the general idea which I tried to give you, that what in numerical they want. So now we need to determine that how much displacement will occur after applying this 10 kilonewton and 5 kilonewton. Also the strain produced in this bar and the stress produced in this bar. So let us begin with the data which are given. We will list it out. So let's understand it here. So what they are giving? They are giving E is the 2 into 10 raised to 5 Newton per mm square. This is given here, which is also equal to E1 is equal to E2 is equal to 3. Why? Because this bar has 3 different segments, 1, 2 and 3. Also the area of this particular part is A1 is 300 mm square. You can notice also the area of the part number A3 is also same, so we will list out as a A3 also the same. Also the length 200, 200 and 200 is for each and every element of the bar is same, so we will list out L1, L2, L1 is this, L2 is this and L3 is equal to 200 mm. Now the first step is that discretization. What is the meaning of discretization? Discretization means that let's say that we are having one bar. Now we want to do a FEA analysis of this bar. So discretization means we will divide this bar into certain number of parts and we will calculate separately for those parts. Let's say in this part, in this bar, you can see this bar is already having a 3 parts. So we are considering here as 3 different parts. Number 1, this one, second number of element, and this is the third number of element. So how will discretize? As you know that this is a one-dimensional bar problem. So what we'll do, we will draw a one line which will represent this bar. So let us say that this is the one line. Okay, this represents a one bar. Now let's find it out that how much number of nodes are there. See, the general theory is that how much number of elements E. Let's say here are the three elements 1, 2 and 3. So number of nodes will be n plus 1. So it will be a 3 plus 1. So it will be a 4. So here are the 4 nodes. First, this is. Then second, you can say here. Third node here. And fourth node will be here. So first node, second node, third node and fourth node. Okay, so I guess it is clear to you all till now. Now let us say that the displacement of this node is in this direction, u1. Then what we'll do, displacement of this node will be u2. Similarly, displacement of this node will be u3. I am just determining u displacement as a node, and u4. So the ultimate stress produced in this element will be sigma 1, sigma 2, sigma 3. Stiffness of this element, let's say this is the element number 1, this is the element number 2, and this is the element number 3. So the ultimate stiffness produced in the element number 1 will be K1, stiffness 2 will be K2, and stiffness 3 will be K3. Similarly, what is given here, F1, because at this point there will be a force 1, at this point there will be a force 2, which is 10 kilonewton according to the numerical. So F2 will be a 10 kilonewton. F3, so in this numerical here also F3 is 5 kilonewton. So F3 is equal to 5 kilonewton, and F4 is also a fixed end, so it will be a F4 simply for us. So this process is generally known as a discretization. So let's say DIS. Okay, so first what we did a discretization of the element, and what we have determined here, we have determined U, which is displacement, then nodes, the number of nodes are here. You can see that this is the first node, this is the second node, third and fourth. Then what we had determined the elements. So where are those elements? These elements are this number 1, element number 2, element number 3. Then what we have determined? We have determined the displacement U, U1, U2, U3, U4. So where are those? The displacements are here, U1, U2, U3, U4. Similarly, we have determined forces F. So here is the force 1, force 2, force 3 and force 4, right? So it is known as a forces. See, it is very simple. You just need to follow these steps only, and you can rewind this video and you can understand that what I am trying to say. And then we have determined the stiffness. Okay, so let's see that which kind of stiffness are here. For element number 1 K1, element number 2 K2, element number 3 K3. So there will be a 3 stiffness. So this step is generally known as a discretization. Now in the next step we will calculate the stiffness metric. So let us give a heading here. Second number, stiffness matrix. Simple. you just need to remember that first I need to discretize, second you need to go for stiffness matrix. Now stiffness matrix is that per element you are trying to find out that how much k will be for that particular element. For k3 how much k stiffness will be there. So let us see the equation. There is very standard equation for the stiffness. It is, let's say, for one element k. So the stiffness for the k will be A area E by L multiplied by the matrix will be 1 minus 1 minus 1 1. It is very simple. So okay, let's note down the stiffness matrix for all three. How it will be? It will be a for the element number 1 k1. So its area will be A1 E1 by L1. For which we are talking right now, we are discussing about this element only right now. Okay, so A1 will be, and yeah, let me finish it, 1 minus 1 minus 1 and 1. So now let's move further. If we put the values of this element, then what it will be? The A1 is, how much A1 is here? A1 is 300 and E is given already, 2 into 10 raised to 5 Newton per mm square. So we will list out that 300 into 2 into 10 raised to 5 divide by length L. So what is the length? Length is 200. So length will be a 200 here. The same matrix I am repeating, 1 minus 1 minus 1 1. Simplifying it, it will get deducted this. So what is remaining? 3 into 10 raised to 5 1 minus 1 minus 1 1. Now I am multiplying this 3 with this matrix. So what will remain? It will remain at 10 raised to 5 3 minus 3 minus 3 3. Okay, so this is the final stiffness matrix for k1. Similarly we will do for the k2 also. So for k2 it will be a k2 a2 e2 divided by l2, 1 minus 1 minus 1 1. And I'm not going to the detail that which values I have put here. You can just see the numerical and just put this value again like that. You need to put that A2 E2 is the same and L2 will be 200. So by putting those values, finally what we'll get? We'll get a 10 raised to 5 in the multiplication 1 minus 1 minus 1 and 1. Okay, so this will be our equation number 2. Let also give our one equation as equation number 1. So this is the equation number 1 for us. Now let's move on further. K3. Similarly, what will get K3? I am writing down the direct answer for the K3. For K3 it will be a 10 raised to 5 3 minus 3 minus 3 3. If you notice that this value and this value are the same, this matrix, and why? Because all the values in the numerical are also same, element number 1 and 3. Area is the same and length is also same, also E is also same. So logically it will come the same answer. Okay, fine. So till this step we have figured out a stiffness matrix. Now what we need to do, we need to find out a global stiffness matrix. So this will be the third step, global matrix. Okay, the global stiffness matrix. Now global stiffness matrix is nothing else, it is the summation of all the stiffness metrics we have found. So K1 plus K2 plus K3. So you can see that, this will be the third equation. So it is the summation of this one, 2 and then 3. Okay, so now let us see that how it will be. It is a very simple rule. If you want to submit out this all the matrices, what you need to do, you need to put it in a diagonal manner. I will show you that how to do it. So the global stiffness matrix will be bigger. Now what we'll do, the answer what we have received from here, this one, we'll put in the extreme up corner. How? So what it will be, 3 minus 3 minus 3 3. Okay, this is the stiffness metric for 1. Another stiffness matrix we will put it here, plus 1. Which one? What about what I am talking right now? I am talking about this one, this stiffness metric, 1 minus 1 minus 1 and 1. So 1 minus 1 minus 1 and 1. And the third stiffness metric, that is K3, it is here, you can see it here, 3 minus 3 minus 3 and 3. So what? Simple, plus 3 minus 3 minus 3 and 3. So I will just sum it up. So this is a total summed all the metrics. So what I will do, final edges I will put it as a 0. Here is also 0, and this row will be a 0, here will be also 0. Now simplifying this matrix, what we are getting, 3 minus 3 0 0 minus 3 3 plus 1 plus 4 minus 1 0 0 minus 1 1 plus 3 4 minus 3 0 0 minus 3 and plus 3. So you can see that this is the global stiffness matrix. And now important thing, what we forgot, 10 raised to 5. So don't forget to put this 10 raised to 5 also. So what I'll do, I'll multiply it with 10 raised to 5. So this is a general global stiffness matrix for us. Okay, so now we have figured out a global stiffness matrix. Now next step is to find out, calculate the load vector. So the next step will be a fourth step. So that will be a calculate load vector. Now load vector is known as a F. So what will be the load vector matrix? Earlier you can check out that how much forces we had in the discretization. There were 4 forces, 1 2 3 and 4. So this matrix will also look like that. What I to do, F1 F2 F3 and F4. Okay, now if I substitute the values of those, it will be a 0 10 5 and 0. How it came, let me tell you. F1 is 0. How F1 is 0 here? See, here this end is fixed. Now if this end is fixed, then what will happen? That force acting at this point will be 0. Another, if F2, so we put the value of F2 is 10 because already in the figure it was given. F3, we put the value of F3 as a 5 kN because it's numerical, and another F4 was fixed point. So what it will be a? It will be a 0. So see, 0 10 5 and 0. So this will be the same matrix for us. And multiplication is 10 raised to 3 because it is in kilonewton. Now we will try to equate this both. How we will try to equate? What you need to keep it in mind, you can see that here is 10 raised to 5. So what I'll do, generally this practice will help you a lot, so you need to convert this one also into 10 raised to 5. So if I will convert into 10 raised to 5, then I need to update these values. So I will update. It will be a 0, 10 will look like a 0.1, 5 will be a 0.05, and 0 will remain 0, and into 10 raised to 5. Okay, so now this both things are equal and together, this one and this one. Okay, so now let's move on further. For further we will go for the step number next. Okay, now we will figure it out a displacement vector. So that will be a fifth step for us. What will be the fifth step? This will be a displacement vector. So let's write it down. Displacement vector. Now displacement vector looks similar to F. So if I will write it down here, you will understand. U1, U2, U3, U4. Is it very simple? So this is the displacement vector. Now sixth step. Now find it out, a stiffness equation. So what it is? Total global matrix, what we found, which we have seen here in K, right? This one, this global matrix is K multiplied by this U is equal to global stiffness matrix. Okay, so this is the global equation. K multiplied by U is equal to F. So what we need to do, we need to put these values here. So what I'll do, first list out the values of K. What are the values of K? 10 raised to 5 multiplied by this, it was minus 3, 3, 0, 0, minus 3, 4, minus 1, 0, 0, minus 1, 4, minus 3, 0, 0, 3, sorry, this is minus 3 and 3. Okay, so this is K. Then the U was very simple, U1, U2, U3 and U4 is equal to force matrix. So we will just replace the value of force matrix which we have obtained earlier, which is here, these values, we will replace it with here. So those values are 0, 0.1, 0.05 and 0. Okay, so now it looks like this equation, particular equation. Okay, and now what we'll do, we'll put the boundary conditions. It is known as a boundary conditions. So if I draw that figure of that bar what we are studying right now, okay, just as a replica to make you understand very easily. So this bar looks like this. This is the fixed end. So now if you talk about this point's displacement, how much it will be? It will be 0, and this point's displacement will be a 0, right? Why? Because it is already fixed end. So we will replace the U1 and U4 with the 0 in this matrix. Okay, so what will be the boundary condition? Boundary condition will be a U1 is equal to 0, also U4 will be 0. Also we had already put those boundary conditions. F1 was 0, F4 was. So now what we will do, we will replace these values in next matrix. So I am just replacing it here. Let's say this is a 0 and this is a 0. So now according to elimination approach, what we need to do, we will cut out all those rows and columns which has a 0 values. Okay, so I am just cutting out this value. See, this is a 0, this is also 0. So this whole row will get neglected, and the first row and first column. Similarly, what is happening, that the last row is having a 0 values. So last row and last fourth column is got disconnected here. So now we can solve this equation with these values, means the left one, which one is here available, this left one values. So we'll write it down in the next step as a separate matrix, and on that base we will find the answer. So what's left now, 10 raised to 5 in the matrix, this one, 4 minus 1 minus 1 plus 4. Okay, this is called as elimination method. Also here what will be, it will be a u2 and u3. So u2 and u3 and is equal to what we are having. Sorry, I forgot to multiply it by this 10 raised to 5. So we are having a 10 raised to 5 multiplied by this, and what it is, 0.1 and 0.05. Okay, so now if I multiply this matrix, this one and this one, I will receive a 2 equations per row. So this will be the first equation. What will be the first equation? It will be a 4 into u2. So 4 u2. Next one will be a minus 1 into u3. So minus, right? So it will be a minus u3. Okay, is equal to, what is this value? It will be a 0.1. So it will be a 0.1. So it will be equation number A for me. Another, this multiplied by this, which one? I'll show it by another color, this. So it will be a minus u2, and this will be multiplied by this one. So it will be a plus 4 u3 is equal to 0.05. Right, this will be our B equation. Now if we solve this equation together, okay, I will try to make any one value out of this equation as a 0. So what I will do, that I will multiply this this equation with the 4. So my 4u3 will be 0. Okay, so what I can do, I will multiply this 4, this with the 4. So what I will get, I will get 16 u2 minus 4 u3, because this 4 will get multiplied by this u3, is equal to 0.4. Similarly, I will just put these values directly here. Minus u2 plus 4 u3 is equal to 0.05. So summation will be a simple for me, 15 u2, this will be a 0, is equal to, this will be a 0.450. So by simplifying this equation C, what I will get? I will get u2 is equal to 0.450, which is here, divided by this 15. So the answer will be a 0.03 mm. Okay, so now this will be the D value. So now simply what I will do, I will just place this value of u2, what value I got for u2 is 0.03, into my any of the equation. So I am just choosing this equation as a standard. So in next what I'll do, I'll write a 4 u2. u2 is 0.03, so 0.03 minus u3 is equal to 0.1. so by simplifying, what I'll get, u3 will be a 0.02 mm. Okay, so now the ultimate answer what I wanted, which I wanted as a numerical standards, I got that is a u1 was 0, u2 which I have received here is 0.03, now u3 which I have received is 0.02, and the final u4, because of fixed end it will be a 0 mm in displacement. Okay, so the first requirement of this numerical was to find the displacement got fulfilled. Now we are moving to the next one. The next requirement, now it is very simple and which is very easy to do it. Now in the next step, what we'll do, now we'll understand the stress in each element. So for that one, there is one very simple standard equation, which standard equation is here. Sigma is equal to E by L minus 1 into 1 multiplied by U1 U2. So this is the standard equation. Similarly, what you can do, we can write for the another one, sigma 1. So that is the stress in 1, so it will be a E1 by L1 minus 1 into 1 and U1 and U2. Similarly, further, sigma 2 is equal to E2 by L2 minus 1 into 1 U1 U2, and similarly for the third element, sigma 3 E3 by L3 minus 1 into 1 U3 U4, and this will be a U2 U3. Why? Because it is the having extreme edges of both. Now just replacing the value of E, L and U. So already we are having the values of E is 2 into 10 raised to 5, L is equal to 200 mm, and U with respect to this. So we'll get the answer. Okay, let's begin with it. Is equal to, let's solve this one. So the value of E is equal to 2 into 10 raised to 5 divided by 200 minus 1 and the value of U, that is U1 is 0 and U2 is a 0.03. so the simplification, we will get a 30 Newton per mm square. Okay, similarly if you simplify this equation, you should get 10 Newton per mm square. It will be a negative, and similarly this one will be a 20 but negative 20 Newton per mm square. You can verify it by pausing this video and you can find it out. So this is the general requirement of numerical, that was stress in each element. The answer of the stress in each element is sigma 1 is 30 Newton per mm square, comma sigma 2 is equal to minus 10 Newton per mm square, and sigma 3 is equal to minus 20 Newton per mm square. Okay, so this is what was required in the numerical, that was the requirement of the stress, which we are fulfilling now. So now we are moving down. Okay, now we are at the last stage of our numerical, that is to find it out the strain. So let's find out the strain. So for the strain, what we'll do, we need to follow one standard equation. Standard equation which it is sigma is equal to E into epsilon, right? where this one is strain, okay, and sigma is stress, and E is already not doing, so I'm not denoting. So now in which we are interested? We are interested in this strain. So equation can be written as sigma epsilon, right, and sigma divided by A. So if I'll write this equation for the first element strain, so it should be like this: epsilon 1 is equal to sigma by E1 and sigma 1. So what was the value of sigma 1? Sigma 1 was 30. So we'll replace it by 30. E, what is the value of E? E value is that 2 into 10 raised to 5. So what should be the answer? Answer should be 15 into 10 raised to 5. But to simplification, what I'll do, I'll write 150 into 10 raised to minus 6. Okay, fine. Similarly, if I'll calculate the epsilon 2, sigma 2 by E2, and the values will be a minus 10 divided by 2 into 10 raised to 5. So the answer should be a minus 50 into 10 raised to minus 6. Similarly, 3, sigma 3 divided by E3 should be a 20. Sigma 3 value is 20 divided by 2. E2 is 2 into 10 raised to 5. So the final solving equation will be a minus 100 into 10 raised to minus 6. So hence the last answer, that required strain in element number 1 is the 150 into 10 raised to minus 6. Strain in element number 2 is the minus 50 into 10 raised to minus 6, and strain in element number 3 is minus 100 into 10 raised to 6. So now we have found out all the answers of this numerical. First, we have found displacement, then we found out a stress, and then we found a strain. Okay, so 1, 2 and 3. So this is how the FEA numerical for 1D bar can be solved by using this technique, and this is in very simple method. Once and twice you need to revise this numerical and do the practice again and again. You can easily solve this numerical anyhow. So that's all for this today's session. We'll see something else, something new in the next session. Till that, goodbye.